In the last video, we saw how to define basic types. So we defined the directions type, which was very simple. It had 4 options, and we used them to construct very simple functions. Today, we're going to have a look at starting to build a deck of cards. So we're going to build a full deck of cards that has some functionality applied to it. But today, we're just going to have a look at the basic element of the suit of the card. So you have diamonds, clubs, hearts, and spades in that order of significance. And we're going to have a look at implementing some type classes on them. First things first, I should define the type. So let's do data, and we're going to call it suit is equal to, and I'm going to order them just for the sake of ease. So we're going to have diamonds, clubs, hearts, and spades. And that's very simple. But if we have a type that we've defined ourselves, we would probably want to apply some type classes to it. As we saw in the polymorphism and higher order functions weeks, it is incredibly useful to be able to apply a type class to a type. So you can constrain its behavior to fulfill at least some basic criteria, in much the same way you would want to implement an interface in Java, whether that's your comparable, comparator, or whatever interface. So how do I do this? Well, let's have a look at defining the most simple type class, or one of the most simple type classes, and that's going to be the equals type class. So I'm going to say instance eq suit where, and this gives us the basic thing we need to define eq for suit. And now I actually have to provide it with the implementation. So now I have to say, how does the suit type implement equals? Well, the easiest way is to start by specifying the cases. So we can start where, looking at the easiest cases, this is when things are equal, and I say true. So this is similar to the guard format where we say something is equal to something, then true. And what I'm saying here is look for this case, and then we go into the next case, which would be the clubs equals true. And I can do the same for the rest. And the reason I'm doing it this way is because at the end we'll be able to use wildcards just to define every other case. So now we just have spades is equal to spades equals true. Now that's all of the true cases. The other case is when none of these conditions have been met. Remember, Haskell checks them in a top-down manner, so it'll look at diamonds and the equals diamonds to see if it's true. And if I get to the end, I can just say whatever you have, if it doesn't meet one of these cases, then it's false. Oh, I've got a little, that's because that should be instance, not instas. And there we go. Now we have the EQ type class applied to suit. So this means that we can compare suits. So let's have a wee look. If we reload this into terminal, I think I've loaded it already, so I can do diamonds equals diamonds, and I should get true. That's good. And let's say if we do clubs, that's false. So that's one basic type class that we've implemented. Now, one thing that we haven't seen so far is the show type class. This is the type class that allows us to actually print things to the terminal. So if I say diamonds at the moment, or something that returns diamonds, I should get, no instance for show suit or using from use of print. That's just because I've hit it into terminal, it's tried to print it, and it says, oh, I don't have an instantiation of the show type class. Now show is just the one that allows you to print to terminal, as I say. So if you have a function that returns a type, you won't have show, so that you can apply that. So let's define that. And again, this is going to be quite straightforward. I'm going to say instance show suit where. And now I just need to go through the cases again. So say show diamonds equals, and now I need to give it a type that it knows how to print. So if I just say it's equal to diamonds, we'll get an error here because it says this is not correct, you shouldn't be doing this, couldn't match suit with type car. So what I should do is I'll return a string, because string already has an instance of show attached to it. So this is similar to when previously in the last semester when you're doing things like compare to, and you apply it to a string because you know it's already instantiated there. That's what we're doing here. We're using the fact that we know that string has a display type attached to it to implement our show. And then I just do the same thing for the last of them. And then finally, for spades equals, and this should just be. So now if I was so inclined, I could define functions which return clubs or suits. But if I go into Haskell and I reload this and then I just type diamonds, now it actually prints it to terminal. So it actually understands now how to do this. Now of course you can do this for other type classes. You can look at whatever type class you want. And you can list these definitions out here. So this allows you to define how these things should be implemented yourself. But there's an easier way. So what we can do is, I will Control X these. As I did in the last week, and I said don't worry about this, now I put deriving show. Now what that means is Haskell can, in some cases, infer the instantiation of the type class for you. So if I say deriving, I have more than one to implement because I want to EQ and show. And I can do EQ and show. And now, without any of that code, I've saved it and reloaded it. So if I reload it, now if I call diamonds, I have diamonds instantiated. And if I say equals, I have that instantiated as well. So while you can instantiate these for your classes, you can sometimes get Haskell to do the work for you, which is great. You can also, if we want to, because if we go into here at the moment and we say diamonds is greater than clubs, because in a deck of cards these should have an instantiation of an ordering. Normally spades is the most the best suit to have. The ace of spades of course being the highest card in most games of cards. Then hearts, then clubs, then diamonds is the lowest. So if I hit this, I'll get no instance of ord because I haven't defined orderable. But if I just come in here and I hit ord, Haskell can infer that for me. So if I say diamonds is greater than clubs, then this should return false. Oh, did I not reload? No, I didn't reload. Then I get false. And if I say that, well, let's say spades, because spades is the highest class, then I get true. So Haskell is powerful enough to infer these instantiations by itself, which is a really useful tool, particularly when you're using simple type classes like this. When you get to more complex type classes, say you're working with traversable or funct or monad, you might want to handle the instantiation yourself, just so you know how it's being implemented. For example, here, ord just takes this ordering here. So it looks at the type, the suit definition and says, okay, diamonds is first defined, that must be the lowest. Then it'll be clubs, then hearts, and spades is the best suit. So Haskell can infer this for you as long as you understand what you're doing. You can get it to do some of the heavy lifting yourself, but it's important that you know how it's working underneath with the instance of where. So that's everything for today. Next video we'll be looking at how to add another type to this. That'll be the rank, so that'll be 1, 2, or 2, 3, 4 up to Jack, Queen, King, and then we'll figure out how to build a deck of cards. So that's everything for today. Hope you found this useful. If you have any questions about this, please do let me know. Thanks.